All right. So uh, I have a number of exercises that I have in mind, and I also received some questions from you. I may start solving them. And if you have any exercises that you request, as I said, if you have any problems in those exercises, I will be happy to help you solve them together. Um, all right, so let's start. Oh, 317. Yeah, actually, I think it was in my list, or let me see. So I will start with 317. And if there's time at the end, and if you don't have any requests, I will try to do it for the exercises that I have selected. All right, so let's start with 317. Shares of company A are sold at $10 per share. Shares of company B are sold at $50 per share. According to market analysis, one share of each company can either gain one with probability 0.5 or lose one with probability 0.5, independently of the other company. Which of the following portfolios has the lowest risk? So this may be about application to finance, or maybe not. Let's try to solve it, whether we can do it with the techniques that we have learned. So we can actually try to compute the expected value of these things and to see what will happen. Okay, I think we can, this is just an expected value question, but let's see whether it's like that. So, 100 shares of A. Okay, so we are going to, with these probabilities, so the expected value, if we compute the expected value of all, we can also do 3.18 after that. If we find the expected values of these things, basically, if we compute the expected values of all these three things, we'll be able to find which one is more likely to get the largest value. In turn, this will basically indicate lowest risk. Okay, the expected values. So uh, one share of each company can either gain $1 with probability 0.5 or lose. So there are two things actually, okay, two probabilities with equal things. So in order to find the expected value of this thing, so 100 shares of A, uh, we can also think about the binomial distribution in this case. It will be like a binomial distribution with probability success rate 0.5 successes. So it will be 50 successes expected here. All right. So the expected value, if you do it 100 shares, but you should also think about the failures in this case because uh, here the failure will affect uh, the failure also will indicate, I mean, you're also expecting 50 failures because failures also, you lose $1. You may expect 50 successes, but what does those 50 successes get you? What is your money going to become at the end? You should try to compute that one. Okay, so here the you're not only interested in successes, because losing failures will also affect our money with certain amount. And the company shares of company A and B, they have different uh, per unit prices, but the loss is not dependent on, it's not a percentage of those unit prices. It's $1 or fixed in both cases. So this will probably affect how they behave. As I said, I think I mean, in order to solve this question correctly, we need to compute the expected value of 100 shares of A. Okay, so 100 shares of A, since each of them is with $10, what we are going to do is, so we have, we can $10 per share. So the expected value of this thing, if it was no loss or no gain, it would have a cost of $1,000, right? So if you look at part A, let me also, I'm just going to copy this to GIMP instead of the annotate. I like the GIMP pen better. So I'm going to just copy this question here onto GIMP and try to solve it there. Um, tools, transform to media. All right. So here, as I said, you need to compute what is the expected value of this variable, 100 shares of A. So 100 shares of A, each share of A, we can also compute the, if we call each share of A AI, or okay. So here, 100 shares of A is basically the summation of these random variables, right? Each share is independent. One share of each company can either uh, gain, okay, but so this is basically the summation we have is when we buy 100 shares of this one, it's going to be like this. Summation of all these things, okay? The 100, if you buy 100 shares, the thing is that each of these shares, they are not independent from each other in a sense that if so, let me read your comment here. If we have one share with 0.5 probability we lose, two shares 0.5 probability, 0.25 probability we lose 0.5. The probability of losses beneath 0.5, I mean, we are not asked the probability here. The lowest risk here, I mean, you're going to lose something, but here when we are asked lowest risk, we are basically asked the lowest amount of money you are going to lose. In other words, if you have, for example, 100 shares of A, which you pay $1,000, if the expected value of this turns out to be 900, for example, and while this one, again, you're going to look at, so we just need to compute not the probabilities, but the amount we lose. Therefore, the difference of the cost we pay versus the expected value of this at the end is going to determine what it looks like. So one thing that is here is that if, okay, when you buy 100 shares of A, there are things that are, for example, if it will be really simple, it will be, for example, if these 100 shares, if for it, I think what this question asks us, ask us to treat each of the share independently because they of this A, then compute the expected value of this thing. But here, I mean, if it wasn't like this, if there's 100 shares, each one with 0.5 probability, we lose $1 for each share. What it's going to be is actually we can also do it like this. If we lose $1, if we buy 100 shares of this, in other words, with 0.5 probability, if we don't treat it like this, each of these shares are going to be down or up at the same time. So if each one loses $100 in total, so at the end it's going to be $900 with 0.5 probability and $1,100 with 0.5 probability. Okay, so we just treat it as the whole shares. A is lost or I mean we lose or we win. If we lose, I mean if the shares A, 100 shares of A with probability we lose $1 per share, okay, so it's per share, right? One share can either gain. So since we have 100 shares of this, if we lose $1, it's a loss of $100 at the end. So here, the expected value of this share at the end is going to be this value. All right. One share of A, risk is, yeah, I mean, yeah, we are going to, yeah, you can also think about it intuitively. The risk here is that, I mean, if you look at per unit risk, you can also do that. The per unit risk, this is $10. The losing of $1 per share, A has more risk, right? So, but here we don't have a choice to get all shares from B. Okay, so buying less A and much B, but here how do you compare less A much B? So this, I think C should in this case should get the highest benefit, the lowest risk, right? So intuitively C should get the lowest risk, but let's compute that this really is the case. So intuitively, you're absolutely right. So, I mean, if you just look at this question, you're losing $1 per share and $50 it is. So it has a low risk. You should get as much as B as possible because 10 has more, I mean, A has more risk. But if you compute this, let's do it. This is like 450. This is, so the expected value turns out to be, again, so since you lose 50%, you gain 50% probability. The expected value here is still going to be the same thing, right? 1000 in this case. Did I do anything wrong here? So you agree with this expected value of A analysis. If you look at part B, this is an expected value of two different things, two variables, expected value of shares of A plus the expected values of shares of B. So we again can do the same thing separately, all right? But what I'm doing wrong here is if I, yeah, it's the 12 shares of B. Okay, so so at the end, if we do, let's do that, compute the expected value, but let's see whether they're all, so 50 shares of A. If I have 50 shares of A, the expected value of that is if 50 times 10, if, sorry, 50 times 9, okay, with 0.5 probability, it's going to you have this value, and with 0.5 probability, it's going to be 0.5. Okay, 50 shares of this. So I did the same thing here, right? Yeah, 100 shares of this. It was, yeah, 100 times 9. Yeah, 100 times 1 was not 100. This was 11 times 100. So plus, so this is the expected value of A and expected value of B. You do the same thing. 50. If you lose one, it's going to be 49 times 1. So by the way, you should also think about the differences you pay here. So so this is going to be, so we get, if you lose with 49, so all of them are going to be the same in this case. So I must be doing something wrong here. So is this expected value analysis correct? So probably we may need to take a look at this one, whether it's correct or not. So maybe we may, the expected value for losing gain, so it's, since they're equal to each other, so the expected value of losing gain is 0. So therefore, when you look at the expected value of everything, you will not be losing or gaining anything. That's the expected value. Okay. Yeah, maybe that's a very good point, Wahab. The expected values will be the same, but what is the variance? Maybe we need to, because when we think about risk, the expected values are all, since that's a very good point. That was the exact point that we were missing. If you just look at the expected values of these things, since the expected value of losing or gaining is 0, whatever your money you're putting, you're going to be getting the same thing. So here, you're absolutely right. We need to consider variance. The smallest variance of these variables, so expected value of this A, expected value of 50 shares of A plus 10 shares of B, and the expected value of, not the we are going to look at the variances of these variables. So let's call this 100A. So the smallest variance 1 is going to have the lowest risk, right? Because if you have high variance, it means that you're likely to lose as well. It fluctuates. Whatever expected value is here, if the variance is large, it fluctuates more. So lowest risk corresponds to here low variance. So we should actually compute the variance of these variables. Yes, intervals of possibilities should be as narrow as possible for us. So Selim is saying exactly the same thing. So we should just compute the variance here. And in order to compute the variance, we need to compute the expected values of the squares of these things. Okay. For example, we can compute the expected, and we can also compute each of them as independent variables like this, and compute the expected. If we have 100 values like this, the variance is going to be 100 times the variance of AI. Okay, and in order to find this, we need to find the expected value of the squares of these things. What is the expected value of the square of this variable? And then subtract from that the square of this 1000. So, and this one is going to be different in these two cases. And here, with these two variables, their variances will be added since they're independent from each other. A and B are independent from each other. Whatever variance we find from 50 shares of A and 10 shares of B, we are going to add those variances. And at the end, the smallest variance one is going to give us the lowest risk option. Yeah, thanks for helping out. Correlation which is negative will decrease the risk. What do you mean by correlation? The correlation between A and B? Here, they're not correlated at all actually, so they're independent from each other. So so I did not understand your comment about correlation. Correlation between A and B is 0 in this case because they're independent from each other. But yeah, I think this question should be answered just like Selim and Wahab mentioned with finding the variance. And for that, we have to find not only the expected value of AI, which is 1000 simply, we have to subtract from this the square of the expected value of the square of this thing. So how do you find the expected value of the square of this thing? What we do is this 900. So in order to find the value of this, the square, each probability should be multiplied with the square, and then so our variable is this. So we need to compute the expected value of the square of this random variable, then subtract from it this expected value square to find the variance. And we do it for both cases, for all of the three cases. So the correlation value, this question doesn't, there is no correlation value in this question. So correlation is out of the question in this question. So you shouldn't think about correlation of these two things at all, because it's in the question it is indicated that they're independent from each other. Okay, so there is no correlation between loss and of company A. Yes, variance is 1 per share. Is it 1? Yeah, here in both cases. So here the variance is 1 per share in each case. That's why we can use when we can use, since this is a linear summation, all these hundreds shares of A, for example, linear is a summation of these random variables. That's why we can use the properties of variance. For example, in this case, for example, yeah, if it's 1, we don't need to compute it as complicated like this. It's going to be if the variance of one share of A is 1, the variance in 100 shares is going to be 100. Okay, and 0.25, let's see. Oh yes, let's see. Okay, here for one share, what we're going to have is with 0.5 probability, it's going to be 9, and so it's going to be 9 square. With 0.5 probability, it's going to be, sorry, with 0.5 probability, it's going to be 11 square, right? So isn't this the variance of a single share of, which is 10, it was $10 per share, right? Yeah, $10 per share. So this is, if we compute this, let me quickly do that. 22.5, and this one 121 divided, so 60.5. So the variance is actually a 83 here, right? The variance in this case, $10 per, so this is the variance of a single share. So what I just computed here was what I computed here was the variance of a single share. If I have a single share of A, this is the variance of a single share, which is 83. If you have this is the variance of the, so you can compute the, okay, I see. So we need to define what our random variable is. Okay, if our random variable here is our gain or loss, okay, then what you need to do is you need to have the expected value of your x in that case will be 0, the expected value of gain or loss. If you want to, it depends really what the variance you're computing depends really on the random variable you're computing. If you define x as your gain or loss, x in this case, you cannot use 9 and 11 in that case, all right? It has to be, so in that case, it's going to be just, this is, you either, this is going to be -1 and 1, and you're going to compute it with 0.5 -1 square plus 0.5 1 square. In that case, it's going to be just like you said, p times q. But here, the variance that I'm computing here is the variance in the prices of share A. Okay, so if you lose $1, the $10 price is going to be reduced to $9. Okay, so with 0.5 probability, we will the shares of A is going to have a value of 9. With 0.5 probability, it's going to have a value of 11 square, 11. Okay, so this variance I'm computing is for the price of, yeah, exactly. You may have multiple approaches for this question. You can, as I said, you can, it really depends on how you define your random variable. Here I define my random variable as the variance in the price of a single share of A. Okay, so in that case, this is the variance, which gives you, if I'm not mistaken here, yeah, this is 81. Oh, I think I am mistaken. Why did I treat it as 45? So this is 81. It's going to be not 22.5, 81. So I just multiply these two things somehow. So it's going to be 40.5, right? 81 divided by 2, 40.5. So this is 6. So here the variance in single share is 101, and the standard deviation therefore is going to be a square of this thing. Okay, so so the so so this is for a single share, $10, right? So the variance in that case, so I think it's too much. I'm making a mistake here. So the price of the single item, the variance, if it fluctuates between 9 and 11, the variance shouldn't be this large, right? So this is the price of this thing. It's 0.5 probability. It's going to be 9. So sorry, this is not the variance. So you should have corrected me that this is exactly 111 is the expected value of x squared. You need to subtract from it this one, so it's going to be so the unexpected value is 10. Therefore, the variance is going to turn out to be 1. So we need to do this. This 100 is the square of the expected value of a single share of A. Therefore, so this is variance. Okay, variance is the expected value of x squared. This is not the variance. This is the expected value of x squared, where x is the price for a single share of A, and therefore variance here is 1. And if you buy 100 shares of this, which are all independent from each other, so the variance of the 100 shares of A is going to be 100. Okay, since the variance of this thing is 100, 1 minus 1. So this is what we have as the variance. Exactly, it's this 111 is the squared dollars. Is the expected value of the squared price of the share A. We subtract from it the expected value, the square of the expected value of share A, which gives us 100. 1 minus 100. It's 1. You're right. The shares of single company should be dependent on each other. So if we can also treat this therefore as a single variable of a price 1000. Okay, that's actually you're right. They should be all dependent on each other, because if we had these 100 shares, they're not random variables. That's another thing. So we should treat this 100 shares of A as a single variable, because it's going to be lost and gained together. So let's do it on a clean sheet here. If you buy 100 shares of A, the expected value, now I define my variable, let's call it SA. Okay, now I define my random variable SA, which is the sum of 100 shares of, so 100 shares of A. Now, the expected value of this obviously is 1000, right? So a single share is this, it's 1000. We have found this one. Now, in order to find the variance of SA, what we are going to do is we are going to find the expected value of SA square and subtract from it this SA square, okay, which is this one, 1000 by 1000 times 1000. So let's, if we do it here, it's going to be, the expected value of SA square is going to be 0.5. If you lose each of these 100 shares lose that, then you're going to have this 900 squared, okay, and plus 0.5, 1100 squared. So this is the final correct approach. So this is the expected value of SA square, subtract from it 1000 square. So this is the variance in 100 shares of SA. And if you take a look at this, So 81. So it's going to be 8100. So sorry, not 8100. 810,000 multiplied by 0.5. This is 405, 400, 5,000 plus 1100 squared and divided by multiplied by 0.5. It is 6.5, so we get something similar. So it's going to be this one, 11, so 1,100,000. Okay, so this is going to be 1,100,000 on here. Subtract from it 1 million, which is going to be 100,000. So the variance we have here is going to be, which is also this $100,000. 100,000. Let me get this. That's the variance is the squared dollars. All right. Therefore, so let me just compute that one. So I can actually directly do it here. Let me use Google. Okay, so it's actually, so your standard deviation is going to be $316. Okay, so what we found here is that if you buy 100 shares of this, so if you have spent $1,000, so your single standard deviation is going to be around 316. Okay, so this is for exactly. So this is the if you add these two things, it's 1.1 million. You subtract from it 1 million. It's going to be 100,000. So the variance of SA is 100,000 squared dollars. If you get the standard deviation, then you may look at the standard deviation is the square of this thing. So your standard deviation is this. So this is the variance you have. So you do the same thing for the other variables separately, and the smallest standard deviation one is going to be your lowest risk option. Okay, so this is basically a variance question and how you compute the variance of these things. Now, so is it clear? Any comments or questions about this thing? Okay. All right, so let's continue with the second. The other request was 3.18. Okay, if you look at 3.18, now if we, instead of these fixed dollars, if we have percentages, the same question actually. Deciding how to invest $1,000. Now we don't have this we have two different things. First of all, the losses and gains are now in terms of percentages, and these are the different profits. It doesn't talk about any losses here. Now we have $1,000, and we have 3 portfolios. Okay, and now we are given some probabilities. The distribution of X. This X, oh, okay, this profit actually, we can also have losses. So these are, this X here, actually it was bad to choose X also as the name of this person. So this X here, the distribution of X is our profit actually. Okay, so it's saying that you may lose 3%, with probability 0.3. You may stay at the same, no loss or no gain with 0.2 probability, and 3% increase with 0.5 probability. Okay, so this is our gain and loss probabilities. And the distribution of y, again the same thing. We either if we buy shares of B, we either lose or gain. We don't stay the same. Now we are going to do exact same thing. So actually this 3.18 is solved very similarly to 3.8. We are going to now, again, we can compute the expected value of these things. Now we have the probability, for example, if we lose 3%, if we get 100 shares of A with $10 per share, we can again, for example, compute the expected values of these things by multiplying the probability with the values of the total value of A when you lose 3% of it. Okay, so this is going to be 0.3 times 3% decrease in the total price you pay. So which is this $1,000. Okay, so it doesn't matter, for example, how many shares you get of this, because if you lose 3%, if you lose 3% of this is 3%. If you lose 3% of this, you lose $30, right? So 917 times 0.3 and 1,000 times 0.2, and if you gain 3%, it's going to be $1,030. Okay, so this is if you add $30 to that with 0.5 probability. So with 0.5 probability, you will be adding, again, instead of defining the your variable as the price that you're going to get, you can actually define your variables as your gains and losses. Okay, because it will, in that case, it will be easier. You're going to be centered around gain and loss. So you may want to choose your random variable. Let's the random variable G denote your gain. Okay, so with independent of whether you have 100 shares of A or not, you have a fixed way to invest $1,000. Okay, so your gain here, for example, with 0.2 probability, you have no gain. With 0.3 probability, you have a gain of you have a loss of $30, and with a 0.5 probability, you have a gain of $30. So in part A, what we're going to do is the expected value of our gain in part A is simply going to be 30 times 0.5 minus 30 times 0.3, right? 0.3. So if you this is going to be 15 minus 9, so our expected gain is $6. So this is what our expected gain is here. We can compute the expected gain in all of these things, but again, just the expected value of the gain is not the only thing we should consider here. We should consider the variance as well. Okay, because your expected gain is 6, but if it has a very high variance, you wouldn't want to invest in that. So if all of the gains are equal, if all of these three options, the expected value of gain is equal, then you may choose the lowest variance one. But if you have high gain but still a little bit higher variance, this is really something to choose manually, whether you want more risk with the benefit of highest gain. All right, so I think these are all about those applications to finance, which we didn't cover here. Actually, this is 3.8. Let's take a look at this 3. Or it was 3.3. Let me see. So what this application of finance is about. It was, so let me application to finance. Next. So it's at the just before families of discrete distributions. So this one also, so this all these portfolio things, so minimizing risk, uh, the the gain, actually they as you can see, they compute the variance, the expected value of thing, the variance of that thing. They all the examples are similar to what we have done, but these are this is not included in the midterm exam. So 3.3.3.8, we haven't covered this in class. All right. So this application to finance is not included. So therefore, we shouldn't think about how to optimize your portfolio, these optimization questions, but it's all about computing the variances. Uh, and here, sometimes, so we have to also the variance of a diversified portfolio. So this is not included, okay? You can also, yeah, it's like binomial distribution too. Yeah, you're right, actually. But here, I think the risk is about variance in that case, because if you look at the expected value of that thing, maybe you can also compute the variance using binomial distribution too. Yeah, so it's possible. So all these different things are related to each other, actually. You may solve different problems with different settings. But yeah, and also we should still be able to solve these questions by using our previous knowledge, by computing the expected values and variances. It's all, there's nothing more here about than computing the variance of these things, and we know how to do those. So I think these are solvable questions. So I agree with you that we can try to solve these questions even if we haven't covered that section, subsection. But yes, if all we need to do is compute the variance and expected value and choose a portfolio based on that. Okay. Any other requests than these? Oops, sorry, I dropped my pen. So if not, I'm going to continue with, for example, I will take a look at 3.6 from chapter 3. Let's look at this one. A computer program contains one error. In order to find the error, we split the program into 6 blocks and test 2 of them, selected at random. Let x be the number of errors in these blocks and compute the expected value of x. So this is an expected value question, but let's see how we're going to do that. You can also consider this. Also, this is like a binomial too, right? You may apply different things at the same time. Actually, we can directly apply binomial to this one as well. So here, if x is the number of errors, what we know is that we already know that the computer program contains one error. Okay, again, let me copy this part to GAMP, and then I'm going to write it there. Let me erase this part and use this slide. All right, let's take a look at this one. Okay, x can either have a value 0 or 1. Okay, the number of errors in these blocks. So we just selected 2 blocks. So there's a program which is divided into 6 parts. 1, 2, 3, 4, 5, 6. And one of these blocks is supposed to contain an error. We know that there's one error in this one. So the probability that a single block contains this error is 1 over 6. All right, so we selected 2 of these 6 blocks. 2 of these 6 blocks is selected, and what is the expected value of the number of errors in these 2 blocks? And here the value x can take, its range is 0 or 1. So what we need to do is this: the expected value of x, we need to compute what is the probability to get 0 errors times 0, the value of x, plus what is the probability to get 1 error in these two blocks. And we are going to multiply that with 1. Okay, so this is how we compute the expected value. This is the value of x0, value of x1, and we need to compute it with the PMF values of what is the probability that x is 0. And if you look at this, in this expected value, whatever this probability is since you multiply it with 0, it has no effect to the expected value, right? You multiply it with 0. So you shouldn't spend your time unnecessarily to find what is the probability to get 0 errors in these two blocks. Although it's not a difficult thing to do, you shouldn't bother yourself computing this, because whatever probability you're going to compute at the end, you're going to multiply it with 0 to find the expected value, since you're asked the expected value. Now, the only thing that's remaining is when we select two blocks, what is the probability that one of them contains errors? So the probability to get 1 error. So here it's basically the binomial distribution where the success probability is 1 over 6. Okay, P is 1 over 6, and we are doing 2 tries. Okay, in 2 tries, how many? What is the probability to get exactly 1 success? So if I just select two things from here, I mean, if I'm going to do 2 tries, the try 1, try 2, the error may be in the first one. In that case, there will not be error here. The error may be in the second one. In that case, the error is going to be this one. So if you remember the binomial, the probability that x is equal to 1 in 2 tries is 2 choose 1. So there are 2 possible cases this can happen. And 1 over 6 times 5 over 6. Okay, the probability to get no error in that code is 5 over 6. This is 1 over 6. No, we cannot get 1 because it contains only 1 error. We are given that we cannot get 1 although it's 1 over 6 in each. We cannot. We will not be. It says we test 2 of them, so we cannot select the same block again. Okay, so we are going to select 2 of these blocks, so it will be another block. Okay, so there will be 2 different things, but the error can be either in one of them, so it's going to be directly like a binomial independent thing. So this is going to be the probability, which is going to be 10 over 36. So the expected value of this thing is 10 over 36. Okay, so the expected number of. So if we had just chosen 1 block, in that case, the expected number will be 1 over 6, right? So this is a slightly larger than 1 over 6. And if you, for example, select the entire 6 blocks, in that case, the expected value of x, we know it's not a random variable. Actually, it's going to be 1 if you choose all the 6 blocks. All right, so this is the expected value. The answer to this question is 10 over 36, and this is how I just use the binomial distribution. So this is P, this is Q. So this is P to the power K, Q to the power N minus K, which is both 1, 1 in this case, 1. Here we wrote this 2 comes from, we are doing 2 tries. Okay, 2 is from, we are not trying 6 different things here. We are going to select 2 blocks. So this 2 comes from the binomial where we are going to make 2 tries, and we need 1 success from these 2 tries. So this is N, this is K, and this is P, and this is Q. So this is exactly the application of the binomial PDF. If we had written 6 choose 2, then we should actually say also, we shouldn't compute the probability like this. 6 choose 2 is the possible ways to choose these two blocks. So it's our total space. So okay, so we could have used some different approach. So this would be a different approach where we first look at solve it combinatorically, not using binomial. So if you choose 6, so this is going to be your entire search space, which is equal to what? 15, right? So this is 15 in total. So out of 15 possible cases, how many of them contains exactly one error out of these? So we are going to find this. So this total is, so I did this right? 6 choose 2. No, actually I did it incorrectly. So 6 choose 2 is 6, 5, 4. Yeah, let me write it. 2, 1, 2 factorial, and 4 factorial. So actually I did it correctly. So 6 choose 2. This one, 3, 15. So 6 choose 2 is 15. All right. Now, this is when you choose two things from 6 things, some of those two choices, they will contain no errors, and some of them will contain exactly one error. So how many of them? So out of these two, all right. So how many of them are going to contain 1, and how many of them are going to contain 0? So here, out of these 15 cases, a number of them will contain 0. So what is the probability that to get 0 ones is 6 choose 5, right? So actually this is the total case. So you need to also look at combinatorically how many different possible cases, how many possible ways that erroneous block is within this 6 block. It can be in either of those. And also, so it's, I think you can, but what at the end, what you need to do is you need to also look at your favorable cases. So this is choosing 2 out of all 6 possible cases is our total space. Now, out of this total space, how many of them contains exactly one error? We should take a look at those. So you can find that, I think, actually how many of them contain no errors at all. I think this is like 6, but is it going to be the same thing here? 6 divided by 50. It seems like it's, if you do it like this, it's going to be like 6 divided by 15. Is it the case? It shouldn't be. There shouldn't be 6 from here. There should be more, right? So what am I doing wrong in the combinatorial way to solve this question? So any ideas here? So here I'm confused at what we're, so this is the total space, but what is our favorable cases? The possible, so actually I need to do to choose something. So here 5 of them contains, oh, out of this 15, 5 of them is going to contain the error. So how did you find that 5? Yeah, so it's the 16, if you divide this 5 over 18. 10 of them does not, yeah, so it's the 10 of them is the different ways we can, so 10 of them does not contain error, 5 of them contains error, so it's going to be 1 over 3, but which is different than what we have here, right? So we should have obtained the same 10 over 36 that we obtained here. So they should even, I mean, if you do an alternative approach, you should still be able to get the same 10 over 16. So the question here is, what is the probability to get exactly one error if you choose two of them? So yeah, if the denominator is 18, I think they become the same. So here 6 to choose 2 out of those 6 blocks. So this should be my total choosing 2 space, right? Which is not 18. I didn't do anything wrong here, right? It's like divide by, so 3 times 5, it should be 15. So there's something wrong here. We may so let me try to take a look at it again by erasing some of this part. I'm going to, where's my eraser? Yeah, here. Let me increase this size a bit. So we have 6 blocks. Let's come back to the 6 blocks. And the possible ways to choose out of these 6 blocks is 6 to choose 2. So this is our the total number of total possible cases, which is 15. Maybe I had something wrong. I did something wrong here, but this is like exactly using the binomial case. The binomial, maybe the problem was that I think, yeah, this is the outcome should be 1 choose 1, 5 choose 1. The favorable outcome here should be here. This is the total number of outcomes. The total number of outcomes here, where we have selecting 2 things. The total number of outcomes is here. The favorable, we have 1 error, and the remaining 5 blocks don't contain any error. So in that case, it's going to be 6. So it's going to be the favorable outcome is 6 choose 1, right? If one of them contains the error. No, it's not. So let's see. Is it, if I do it like this? Yeah. Why is it 1 choose 1? The favorable outcome, because in that case our favorable outcome is just 1, but so one of them contains, but we are choosing actually the 6 choose 2, so we are choosing these 2 cases. So what we can have here is that if you look at these 2 things here, the probability that none of them contains so the probability that one of them is going to contain this 1 over 6. So it's I always go to this binomial case. So it should be yeah, this times 5 choose 1, which is going to be 5 in this case. So 5 of them. Yeah, you're right. This is how we obtain the favorable. So 5 choose. If you multiply, so 1 of them contains this, and 5 of them. You're right. And 5. So this is what we do exactly. You're right. So the favorable case is that we have 2 of them. We want 1 of them to have. So it should be like this. You're right. So this is our 2 choices. 5 of them, choosing 1 from those 5, and choosing only one of them contains our error. You're right. So we should exactly do that. Exactly. So this is the number of favorable cases. In that case, we should get 1 over 3 as the probability to obtain 1. But we didn't get 1 over 3 here. Slightly lower than 1 over 3 because I think maybe the binomial case treated that as 2 independent things, 2 independent trials. So we're not doing independent trials here, right? If we select one of them, and and it is, for example, so exactly binomial shouldn't apply here. So the way we computed the probability using binomial, in order to have binomial, uh, x is equal to 2 also should be possible, right? When you do 2 tries, that was that was our wrongdoing. So when you use binomial, when you have two, when you do 2 tries, uh, with each success probability 1 over 6, x is equal to 2 is also a possible outcome. But in our case, x is equal to 2 is not possible. So we shouldn't solve this question using binomial because these trials are not independent from each other. If you get the success in the first case, you cannot get another success in the second try. That's why binomial is not applicable to this question. So we should really use this combinatorial approach and find the favorable outcomes out of these 2 tries. 5 of them do not contain error, 1 of them contained error, and then the total number of outcomes is 15. So we should compute the probability that x is equal to 1 using combinatorics in this case. In order to have binomial, the different trials should be independent from each other. In this case, when we, since x cannot be equal to 2, binomial doesn't apply in this case. So the correct solution would be the expected value of x should be 0 times whatever the probability of obtaining 0 things, and 1 times probability of obtaining 1. In that case, its expected value is going to be 1 over 3. All right, thanks for the help. So this was question 3.6. Let me continue with 3.7. I'm not going to have a break today, so let's spend all our time. If you want, you may even I may even stay at our office hour at 1:30. Okay, so I'll be if you request, if any one of you send me an email to have your questions asked, I will be here in my office hour at 1:30. All right. So another question that I have here is 3.7. This is again about expected value and variance. So the expected value of binomial distribution is, in this case, the expected value of x here. The binomial distribution this is going to be the same thing here, right? Yeah, it's like the expected. When we do the favorable outcome, we get the same thing, 1 over 3. But yeah, thinking about this as binomial, the expected, it seems like we get the same thing as the expected value of the binomial, which is n times p. N is 2 and p was 1 over 6. It may be coincidence, you're right, because as I said, this question shouldn't be solved with binomial because these 6 different parts of this computer program, when we have an error in one of them, again, when we, for example, have 6 tries, if somebody says you look all 6 of them, again, the expected value is 1, but the binomial variable could have x is equal to 6 if you do 6 tries. We cannot have 6 in this case. So therefore, these different trials are not Bernoulli trials, which are independent from each other. That makes this, so this number of errors in these blocks, we cannot use binomial here because they are not independent trials. If we find these are the 2 possible values our random variable can get. In binomial, in 6 tries or in 2 tries, we could get 0, 1, 2, or 2. Therefore, we will be representing our probability space differently if we use binomial. This may be a coincidence in this case, you're right. So if you look at this, the second exercise, the number of home runs scored by a certain team in one baseball game. So this is also the expected value and variance question. So we are going to, here, the different thing is that we have a variable, which is two games which are independent from each other. So we need to also find the expected value of a summation. But since these are independent, if you find the expected value of a single game and the variance of a single game, you can just find the expected value and variance of y by multiplying it by 2. Okay, so since there are two games which are independent from each other, the expected value of y will be 2 times the expected value of x, and the variance of y will be 2 times the variance of x here again. So how do we compute again the expected value? 0 times 0.4 plus 1 times 0.4 plus 2 times 0.2. So the expected value of a single game is 0.44, right? So let me, so it should be so 0.4, and this one is also 0. We multiplied by 0.4, so it's 0.8 in total. So the expected value of x is 0.8. The expected value of y, therefore, is 0.8 times 2, which is 1.6. In order to find the variance, we need to multiply these probabilities with the squares of these things. So 0.4 comes from here. 4 times 0.2, it's going to be 0.6, right? In this case, so what is the expected value? So expected value of x squared is going to be 4 times this, which is 0.8, and this is 0.4 again, which makes 1.2. 1.2 is the expected value of the square of this thing. We have figured out that the expected value of this one was, let me also write these things down again. So with this, let me quickly just copy this table. All right, so, okay, so the expected value of x we find as 0.4 times 2 times 0.2, which is equal to 0.8, right? And then therefore expected value of y is 1.6. Now the expected value of x squared, on the other hand, is 1 squared times 0.4 plus 2 squared times 0.2. And what I have here is 0.4 times plus 0.8, which is 1.2. So this is the expected value of that thing. So the expected value of x was this. So the variance of x, on the other hand, is going to be 1.2 minus 0.8 squared, which is going to be 1.2 minus 0.64, which is going to be 66, yeah, 56, right? So yeah, 0.56, and therefore the variance of y is going to be 2 times 0.56, which is 1.12. So this is how, I mean, if you just find the variance of the single entity, it's just going to be fine. Now, actually, I want to move to chapter 4, where there are some interesting questions that I have, which are, so in chapter 4, for example, this question, which actually uses our previous knowledge. Actually, I think it was at the end of chapter 3 too. Yeah, not chapter 4. This was mostly, so this is still chapter 3, sorry, but I'm going to now move on to some interesting questions, like 3.35 is an interesting question, which is like also a Bayes type of question. It doesn't look Bayes at first, maybe. So this 3.35, let me solve that. And there is another one that may be interesting. Let's see. Oh no, 3.35, and then I'm going to move chapter 4. Let's look at this. In some city, the probability of a thunderstorm of any day is 0.6. And during a thunderstorm, the number of traffic accidents has Poisson distribution with parameter 10, which is lambda is equal to 10. All right, so which is 10 accidents, 10 traffic accidents in a day. Otherwise, the number of traffic accidents has Poisson distribution with parameter 4. So if there's no thunderstorm, there is 4 accidents per day. If there's thunderstorms, there are 10 accidents per day. Now, if there were 7 accidents yesterday, what is the probability that there was a thunderstorm? Okay, so let me write these things that are given to us here. The probability of a thunderstorm is 0.6. So the probability that thunderstorm, we can have this variable t to indicate that there's a thunderstorm. When it's 0, there's no thunderstorm. So this one is 0.6. And the probability that, it's not probability, the number of accidents is a Poisson with lambda is equal to 10. It has this distribution when we know that there is a thunderstorm, and when there is no thunderstorm, it has a different the same number of accidents has a different distribution with lambda is equal to 4 when there is no thunderstorm. Now we are asked that we are given that this x is equal to 7, and what is the probability that there was a thunderstorm given that x is equal to 7, right? We are asked this. So how do we solve this? Because conditionally, we are given, as you can see, these two things that are given to us, they're not given to us directly as probabilities, but you're given as distributions, the Poisson distribution. But we can find that what is the probability of x when lambda, we have a Poisson distribution where lambda is equal to 10, and what is the probability of x being equal to 7 if it was a Poisson distribution with lambda is equal to 4. So in order to solve this question, we need to just first write our Bayes rule, which is the probability of x is equal to 7 when there is thunderstorm. Sorry, not this one. X is equal to 7 given that there is thunderstorm plus the probability of thunderstorm, all right, and divided by probability of x is equal to 7. All right, so the probability of x is equal to 7 is also not given to us, but we can also find that by total law of probability. So what we are going to do is that the denominator here is going to be repeated. Actually, the numerator is going to be repeated in the denominator, which is like this, where we have thunderstorm divided by the probability of x is equal to 7 when there is thunderstorm. Oops. It's a conditional probability plus thunderstorm, and plus the probability of x is equal to 7 given that there is no thunderstorm plus the probability of times the probability of t is equal to 0. Okay, so we have to, so this is the solution is written here, and it directly comes from Bayes. So how do we solve this? First of all, the things that the conditional probabilities here, when there's thunderstorm, what is the probability of x is equal to 7? This is directly Poisson PDF or Poisson PMF, where lambda is equal to, when there is thunderstorm, lambda is equal to 10. What is the probability of x is equal to 7 when lambda is equal to, so this is directly that value. We just find the probability mass function for x is equal to 7 when lambda is equal to 10. That is that probability. We multiplied whatever we find there. We multiply. Let me see whether I have that. So actually, I don't have these values with me. So we can actually use Octave Online to do that. So let's do that as well. Possum, PMF, MATLAB. Let me see the function name first. So you write X first. Another, Sibel Hoca shared a post with you saying that if you're going to use MATLAB, Octave Online, you should be really careful about what these variables mean. For Poisson, it's okay. It means lambda. Especially, you need to be careful when you're using exponential CDF. In exponential CDF, for example, the lambda is not provided as a parameter. It actually gets mu, exponential CDF MATLAB. So if you take a look at this, it says if you're going to use the exponential CDF function for MATLAB, you don't see lambda here. You see mu, which is actually 1 over lambda. It's the expected value of waiting time in exponential distribution was 1 over lambda. So whatever lambda is given to you in that question, we have seen in the book that lambda is the parameter of exponential distribution, but the MATLAB function CDF does not get the parameter as one of the inputs. It gets mu, which is the expected value, which is 1 over lambda. So you should just write as your second parameter 1 over lambda. So the Poisson PDF is simple. It just gets x and lambda. So let's go to Octave Online. Let me load the package. Package load statistics. And Poisson PDF. 7 accidents when we have 10 as lambda. And then another is 7 accidents when we have 4 as lambda. Okay, so these are the probabilities that we are going to use. So we are going to, So this one is going to be multiplied by 0.6. Okay, so let me directly try to compute it in Octave Online. So this one, our answer therefore, Poisson PDF times 0.6, the probability that we have a thunderstorm, divided by this exact same thing. Let me just copy it here. This one plus Poisson PDF 7.4 times 0.4. So 0.4 is the probability of no thunderstorm. When we have no thunderstorm, this is the probability of no thunderstorm, and the probability of x is equal to 7 given that there are no thunderstorms. Okay, so this one, I think I need another parenthesis here. So yes, let me see. So yeah, I need another parenthesis here. So the answer to our question is 0.6. So the probability, so wow, did I do something incorrectly here? 7.4. Oh yeah, I did something incorrectly. So this one, why did I use 4 here? Because it should be 10. I copied the wrong thing. So it should be like this. It's solved. So if you're, as you can see here, you shouldn't use, I mean, it was all same lambda. So I used the wrong lambda here. Yeah, the first one should be this one, also one of the things in the denominator. So when there is thunderstorm, this is the probability of thunderstorm. When there is thunderstorm, lambda is 10. So it should be this one. So our probability, the probability that there is thunderstorm is 0.69. So it's actually larger than, so 7x larger than the unconditional probability of thunderstorm, which was 0.6. Unconditional probability of thunderstorm was 0.6. And the condition, it means that having more accidents, observing 7 accidents, if you look at these probabilities, 7 accidents when lambda is equal to 10 is more likely then 7 accidents, it was the probability was 0.09. And the probability of 7 accidents when lambda is equal to 4 is 0.05. So we are basically the computing the probability. If you were computing the probability of likelihood, we would just directly um, take the ratio of these things. But this is not the likelihood. We're asked the probability. Therefore, what we need to do is we divide this thing by this plus this. All right. So this one basically gives us, since observing 7 accidents when lambda is equal to 10 is larger, it increases our belief of a thunderstorm in that day. It's now increased to 0.69% of probability. All right, so that's one problem which is, I think, interesting, which is in chapter 3. It also requires you to use Bayes at chapter 3. There's one such other interesting question that I was asked, which was chapter 4 and question 30. So this is also interesting, where we have two different distributions for something. For one variable, we have two distributions. So how are we going to solve this? So let me copy this one. For 30, I'm copying onto GIMP. All right. Okay. Now, we have an internet service provider with 2 connection lines for its customers. 80% of customers are connected through line 1. So there are 2 lines, and 20% are connected through line 2. So 0.8. So it's like probability to be in line 1 is, or let's call this, let's call L the variable that shows you which line you're in, which can get 2 values, 1 or 2. Okay, so this becomes a random variable in this case. It's not an event. But the probability that this random variable which shows your line number is 1 is 0.8, and probability that your line number is 2 is therefore 0.2, right? So the first sentence, actually the first 2 sentences gives us this information. Line 1 has a gamma connection time with parameters alpha and lambda equal to these values. Okay, alpha is equal to 3, that's for line 1, and lambda is equal to 2. Line 2 has a different distribution, not even gamma. It is a uniform connection time with A is equal to 20 and B is equal to 50. Now, compute the probability that it takes a randomly selected customer. So what is the probability that the connection time is going to be more than 30? This is what we are asked. Okay, so this is like the unconditional. You're asked here in this case an unconditional probability. This is not about the Bayes rule, okay? But how do we compute this thing here, the unconditional probability of the probability to get more than 30? This time we're going to use the law of total probability. Actually, the probability that the connection time is going to be more than 30 or if you think about the outcome space, the line can either be 1 or 2. There is no other line, okay? Line 1 and line 2. So we are going to actually add these probabilities. What is the probability that t is greater than 30 when line is 1 and L is equal to 1? So that's one event. The other event which we are going to add is the connection time greater than 30 and line is 2. Okay, so if you look at these 2 events, they are this line 1 and line 2, first of all, line 1 and line 2 are mutually exclusive events, and they're exhaustive, as you can see. The total probability adds up to 1. There is no other line. So they're mutually exclusive and exhaustive events. And so we can therefore, since they're ended here, we can add these probabilities directly. They have no union. Something cannot be at the same time. One connection cannot be at the same time line 1 and line 2. So their intersection is empty set. Therefore, these probabilities can be added directly. And this is what we are asked. The probability to connection time greater than 30 is given by these two things. But how can we compute these intersections? What is the probability that t is greater than 30 and L is equal to 1? We do that by using the definition of conditional probability. So this is an intersection. What is the probability that line is 1 and time is greater than 30? This is basically probability that time is greater than 30 given that line is equal to 1 times the probability that line is equal to 1. So this conditional probability, gives me this probability that I'm looking for. And I will add to that the probability that t is greater than 30 given line is equal to 2 plus the probability of line is equal to 2. So intuitively, if you see that, we are going to compute the probability that the time is going to be greater than 30 in both of these distributions. And we are going to get a weighted average of these probabilities. So we are going to compute this probability first and then this probability second. And these probabilities are going to be weighted by their line probabilities, what the probability to be 0.8 and 0.2. So the solution is actually really intuitive in this case. So the second one, line 2, uniform distribution is really simple to compute the probability. So the entire duration is like 30 seconds. And the probability that is going to be between 30 and 50, this is going to be 2/3, right? So the entire 30 seconds, so the probability that t is greater than 30 is the 20 divided by 30, which is 2/3, 2 over 3, which is 0.666. We are going to multiply this with the probability to connect through via line 2, which is 0.2. And we are going to compute the gamma CDF. So it's going to be 1 minus CDF gamma this is 2 minutes, so it's given to us as 2 per minute. We should first maybe convert it to seconds, or we can also convert our second units. 30 seconds is half a minute, right? So we can also convert it to x value here will be 0.5. So 30 seconds is 0.5 minutes. So we can ask what is the probability for the waiting time to be less than 0.5 minutes, and take 1 minus 1 of that CDF gamma. So CDF gamma alpha is equal to 3, lambda is equal to 2, with evaluated at 0.5 minutes. So this is the probability. What I write here is the probability that it's going to get less than 0.5 minutes. That's the probability. 1 minus that will be the probability to wait more than 0.5 minutes. And you multiply that with 0.8. So if we do that, what is the CDF again? Let's see how we can do it in gamma CDF MATLAB. Gamma cumulative distribution function. So it has gamma CDF. So what is this A and B? So we should look at what these ABs are. Yeah, it's probably 1 over lambda. This is shape and scale parameters. Wow, so we need to go back to the book to say what alpha was the, I think it's, yeah, it's going to be But we need to be sure really what this shape gamma distribution. Oh, which is equal to the product of the parameters. So yeah, if it's the, yeah, it's exactly here. B is 1 over lambda because it's say the mean of the gamma distribution, the expected value of the gamma distribution, it says it's equal to the product of the parameters. So therefore A is alpha, B is 1 over lambda because our expected value in gamma is A over lambda. So exactly, we are in this case we are going to be looking at, I'm directly copying it here, gamma CDF. So this is the probability. So we are going to be using 1 over 2, 1 over lambda here as your as our parameter B, and our alpha was 3, and x we give it 0.5. This becomes our probability. So what we need to do is multiply this with 0.8 and add to that 2 over 3 times 0.2. So that's our probability. So the answer to this question is 0. Oh yeah, exactly. I forgot that. This was the CDF 1 minus, you're absolutely right. So this was, we should do it like this, which is going to be 0.8691. Okay, so this is the probability that it's going to take more than half a minute. And this is line 1, and this is the probability to take more than 30 seconds in line 2. So the answer to question 430 is therefore this. Okay, so are there any requests from chapter 3 or chapter 4? Do you want me to solve? We still have like more than 15 minutes. I will try, I may solve some other problems, or if you have a question other than the exercises, that's also fine. If not, I may go ahead and try to solve some random questions from this at the end of chapter 4. Oh yeah, there's the gamma Poisson formula. Yeah, let's solve one question about the gamma Poisson formula. Does anybody know any exercises about the gamma Poisson formula here? Let's try to do that. Let's try to figure out which one. Standard uniform geometric distribution. Some. It's okay. Yeah, the gamma Poisson formula. It's okay to solve them without transforming too. You can directly use the gamma CDF. Since MATLAB and Octave directly has the gamma CDF, it's okay to compute them. But if in the question, I mean, some of these things, for example, the gamma Poisson formula is not an approximation. It's an exact thing. Some of these are approximations. For example, the normal approximation to binomials. If it means that when we have some approximation, we use approximations like this. If in the midterm, if in the question it states that use this approximation to solve this question, please do that. All right. So because there will be differences if you don't use the, for example, if you say that use the normal to binomial approximation, if instead of using normal, if you try to compute the probability directly with the binomial, you will get probably a different answer. Okay, so when we talk about these approximations, if it will be indicated in the question. So when there are multiple things that you can do in the question, for example, if you could use normal approximation, it will be indicated in the question specifically to use the approximation or not. All right, so please take extreme care into these. If the question asks you to use a certain type of method, use that. But otherwise, as in this gamma Poisson formula, you can use different things. And also solving negative binomial questions. In the book, the negative binomial, there's an example in the book where the negative binomial is converted to binomial and solved. You can either do that Or if you're going to use the negative binomial of MATLAB or Octave Online, you should be extremely careful because the random variable for negative binomial and the geometric distribution also, they are defined differently. It's not the number of trials that is defined, but it's the number of failures. I think it's a more number of failures, maybe a more standard way to define this, but there is no uh, common thing about it. In some statistics books, geometric variables or negative binomial variables are defined as the number of trials. Okay, but in Wikipedia, for example, if you go to take a look at the Wikipedia article on negative binomial distribution, it defines the random variable as the number of failures to get 5 successes, for example. It's not number of trials, number of failures where you get, for example, 5 successes. So therefore you need to pay extreme care on these issues, how those random variables are. But those are the only things that I could come up. Yeah, you can also, of course, you can. The number of failures, case, and trials can be converted to each other logically. It may even be easier than conversion from negative binomial to binomial. There was an example in the book about negative binomial to binomial, because the number of successes and failures is just the number of trials is the summation of them, right? So if you know number of trials is that, you just subtract the number of successes from the number of trials, you get the number of failures. So they can easily be converted to one another logically. But you should be careful. Just know that you have to convert them. It's not so difficult to convert, actually. The number of trials, converting it to number of failures, you just need to subtract whatever the number of successes you're looking for. Number of successes is the parameter in negative binomial. So you just subtract that constant number from the number of trials that you're asked. Should I solve, for example, for 31, or yeah, what about for 32? It's about expected times. So 2 independent customers are scheduled to arrive. So you were going to solve gamma Poisson formula, and 4.9 we already solved it, I think. But yeah, we can. So this one was a gamma Poisson formula, or is it the example? I mean, on the slides actually we just solved the examples, right? In terms of exercises, we didn't solve any exercises. But let's see whether we have a gamma Poisson here. If anybody has come up with a gamma Poisson type of exercise in the exercises, we may do that. So this one is a gamma distribution. Yeah, actually we can do that within the first 6 months. Or but we can directly also use the gamma CDF. But let's try to solve 4.8. Okay, so this one is gamma. This one is exponential. Yeah, I think this one is 4.8. We can solve 4.8 here. So we have alpha is equal to 2 and lambda is equal to 2. Compute the probability that the component fails within the first 6 months. So this is good. The component, so here in the gamma Poisson formula, again, let me just copy it because I'm going to do some writing on GAMP. Let me copy it here. Okay. All right. So we have a gamma variable, let's call it G, which gives us the waiting time, right? So here we are asked, what is the probability? So let's call this T as the waiting time, and my variable P is going to be the number of events. Poisson is the number of events, which is discrete. T is here gamma, which is continuous. So T has this parameter alpha is equal to 2 and lambda is equal to 2, and it's given as years. And we are asked what is the probability that the component fails within the first 6 months. So the probability that T is less than 0.5 in terms of years. Okay, so simply when we have Octave Online or MATLAB in our hands, all we need to do is do this with the gamma CDF 0.5, 2, and since lambda is 2, we are going to give 1 over lambda to that, so another 0.5 here. Okay, so the multiplication of these two things should give you the mean number of years, which is 1 here, alpha over lambda. So the solution to this question, this exercise, is directly the gamma CDF. But let's see whether we'll be able to obtain the same thing by using the gamma Poisson formula. So the component fails within the first 1 month. All right, so but within the first 6 months. So in order to use the Poisson formula, we should first convert our lambda to this Poisson variable. So since this Poisson variable is 6 months, we need to now see what is the lambda in 6 months. So this lambda was 2 events per year, and so lambda for this Poisson variable, for P, let me write next to this, lambda is going to be equal to 0.5, which was that RT, times the original lambda here. What I'm doing is lambda T, which is going to be 1. So in 6 months, we expect 1 event to occur. All right, so what is the probability that the Poisson variable here, since it's going to fail within 1 month, so the probability that this Poisson random variable is greater than or equal to 1 in this 6 months, right? So we are looking at this thing. So the probability that our Poisson variable is greater than or equal to 1. What is the probability to obtain 1 or more failures in 6 months? Which can be computed by what is the probability. So 1 minus, if we do, what is the probability to obtain 0 events? Okay, so if you look at this, if you know the probability of obtain to 0 events in 6 months of time, if we subtract 1 from that, we are going to be finding what we are looking for, right? So this is oh, the component fails within the first 6 months. I forgot that alpha is 2. Okay, so in gamma Poisson formula, in order for the component fail, there should be 2 failures. Okay, so that's really important, not 0 failure. We need to, in order for the component to fail within first 6 months, we should have 2 or more failures within 6 months. So the probability that I have to say was the probability to have more than 2 or more failures within that interval. And therefore, what you have written there is correct. If we figure out what is the probability to obtain 1 or less, not fail, the probability to not fail within first 6 months is to have alpha minus 1 here, 1 or less. So it's going to be lambda, the Poisson CDF. So Poisson CDF, where we will be looking for what is the probability to obtain 1 or less failures with our lambda in 6 months. The probability to obtain 1 or less failures in 6 months is going to be this. And the complement of this thing will be the probability to obtain 2 or more failures. So these two things should be equal to each other. Let's check that. gamma CDF 0.5 to 0.5. So 0.5 to 0.5. So this is our formula probability that we've computed by using that. And Poisson CDF 1, 1. So they're exactly the same probabilities, as you can see. It's not an approximation or anything. So this one is just showing how we can use the gamma Poisson formula to solve the same thing in both ways. But as I said, this may be not necessary for you if you don't. I mean, even if you ask directly to use the gamma Poisson formula to do this, but if you're just asking a numerical number at the end to enter in the exam, you don't need to do that, okay? Because gamma CDF they're equivalent to each other, so they should give exactly the same probabilities. All right, so that's one gamma Poisson example. Any other exercises that you want me to solve, or any other questions or any difficulties when you had when you were trying to solve exercises? Okay, I think there are no requests, so I think we may. Oh, the last parameter, exactly. It's not the expectation. The last parameter in gamma CDF. Here, let me go back to here. The last parameter here is 1 over lambda. The expectation is A times B. So here it's written here. The expectation. Oh yeah, I'm recording the lecture, so I will put the lecture, the entire lecture on YouTube and directly give you the link in 1 hour or so. It will be in the same playlist. I will not share it with the link again, but yeah, I will put it into the same playlist in 1 hour. So we are recording the lecture from the beginning at 9:40. So the expectation here is not B, the second parameter of gamma. B is actually the 1 over lambda. It's like the expectation of the exponential distribution. So the relationship, if you remember, gamma is a summation of exponential variables. Both in gamma CDF and exponential CDF, they use 1 over lambda as one of the parameters. So this B here is 1 over lambda, and A is your alpha. So A times B is the expectation of the gamma random variable here. So yeah, 1 over lambda is the scale parameter. That's good. And the alpha is the shape parameter. So when alpha is the shape, so the book actually tells that if you just see that when you look at this, if you read this description, the shape parameter is A and scale parameter B. So if the book says alpha is the shape parameter and 1 over lambda is the scale parameter, you immediately know B should be 1 over lambda and A should be alpha. Tomorrow, I will not have an office hour before the exam, but if you need that, I can actually have I have time tomorrow. So in the exam. Okay, so yeah, actually in the exam all the questions will be on one page, so scrolling will be iterating over questions. So all of the questions will be on some single page. You can do them in any order and you will see all of them simultaneously. At the end of the exam, if the time expires before you submit your attempts, they will be automatically submitted. Okay, so there will be 14 questions. So in 2 hours, so you will have about 8 minutes per question. I solved all of the exam from scratch myself. Since some of the questions were random, I had to solve them on my own. I did some mistakes, stupid mistakes too. I got like 85 from the exam myself, but I was able to solve the entire exam in half an hour. So it shouldn't. I mean, but since I prepared some of the questions, I knew some of the questions, so that may be a way too fast. But 2 hours should be sufficient to solve those 14 questions. Take your time. Do not rush. At first, all those 14 questions may seem a lot, but 2 hours is also a long time. And with this MATLAB available to you on Wolfram Alpha, if for integral derivative type of, if there are questions like that, you can use Wolfram Alpha to do that. It has definite integrals that you can integrate directly from some point to some point. You can give any function to that. So Wolfram Alpha is really good as at derivative and integrals. You can do that. And you have also Octave Online for PDF, CDF type of stuff. So I think, yeah, 2 hours is going to be enough for you. We believe that it's going to be enough for you for those 14 questions. And yeah, and during the exam, I will take a look at my emails. I will check my emails regularly. So if you have any problems during the exam, send me an email and I will get back to you as soon as possible within 5 minutes or so. All right. So, and today, if there is any request, so by default, I'm not going to have my office hour, but but if you have any questions, please let me know and I will conduct an office hour also at 1:30 today. Okay, but if there's no emails, any request from you, I will not conduct an office hour. So if you didn't send an email, you may want to check in if we are meeting or not. If there's no meeting at 1:30, you're free to join and leave anytime this Cisco WebEx meeting room. But if you need an additional office hour today, I will be happy to meet with you at 1:30 as well. All right. So yeah, I didn't stop the recording.